Okay, in this video, we are going to be looking at what it means to find the area under a curve, and we're going to do a couple application problems along with that as well. But first of all, when we're finding the area under a curve using calculus, you're finding an infinite number of little slices of that curve. So we have to talk about what that means in terms of the summation. So first of all, we have this notation called sigma notation. So this right here is the sign for sigma notation. Now sigma means the sum of all numbers, right? So that's what it looks like an E, and eventually that's what the integral sign, so the integral sign comes out of that. So instead of adding each individual part, the integral sign adds all of them together, each all at the same time. So we'll get to that. So first of all, the sum of the n terms is written as the sigma notation is I is equal to 1. So this right here, the I, that means or represents the index of summation. Now, we are not going to be getting too much into that, but basically when you break up your curve, you're breaking it up, like let's say from 1 to 5, you break it up into 5 equal rectangles. That would be your indexes to 5 parts, but we're not going to get too much into the specifics of the index and the sigma notation right now. And then the a sub I, so this part right here, that is the I or nth term. We're used to nth term, but since I is your index, and then these are your individual terms. So these right here are your individual terms. Okay, and then the n, that is like the nth term. So if you're adding them all the way out to 100 or 1,000, whatever that might be. And then the upper and lower bounds, so right here and right here, that's a 1. It kind of looks like an R. Those are the upper and lower bounds. So n is the upper bound, and 1 is your lower bound. I mean, you start by plugging in 1, and then you plug in 2, and then 3, and then 4, and then 5, and then 6, all the way to n, whatever n is. So that is your nth term. Okay, now let's do some examples. So let's do this first example together here. And this is your first term. And this is kind of your function, what it's going to look like when you plug it in. And we go all the way to I equals 6. So we plug in 1. And remember, this is summation. So sigma means summation. So you plug 1 plus the summation. Then you plug in the next interval value, which is 2 plus 3, then 4, then 5, then 6. And we add all of those together. Now, a quick way to add a string of numbers with equal intervals is you add the first and the last, and then the next, and then the next. See how many pairs there are? So that's 7 times 3 pairs, and then that is 21. Okay? Later on, when we learn to integrate, the math will do all of that for us, and we won't have to do it, which is really cool. So this leads into that idea. So go ahead and try the next two. Try B and C on your own. So pause the video, try those, and then come back. On the first one, plugging those values in. 2, so you plug in 0 first, and then you plug in 1, and then 2, and then 3, and then 4, and then 5, because 5 is your upper bound there. When you plug those in and then simplify, so 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1, you end up getting the same string of numbers, which we already know adds up to 21. The second one, you would start at 3, end at 7. and you would plug those in for j here. So it would be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And remember, we know we're adding because this whole thing implies a summation. So you're adding this sequence of numbers together, and then when you add those together, you get 135. Okay, so for this one, now the 1 over n is representative of a sort of function, and so you don't have values to plug into n unless you know what value you are going to, which we don't. So what we're going to do is we're going to plug these values in for k over and over and over, and since 1 over n is the common multiple, you can leave that out front if you wanted to, or you can just include it in every part, the series or sequence part. So for example, it would be 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1 plus 1 over n times 3 squared plus 1. And you can see how this is going to go on and on and on because we don't know to what n value, right? So we keep going on, then out to infinity, it would be 1 over n times n squared plus 1. So this would be your nth term right here. Okay, and we can't get numerical values because we don't necessarily know what that n number is. For this last one, you're just plugging right in there into your x sub I. So you're going f of x sub 1, change in x or delta x, plus f of x sub 2, change in x, plus f of x sub 3, that's a 3, change in x, all the way out to f of x sub n, change in x. So again, you're just plugging whatever that term number is now into whatever the function is, because curves aren't always whole numbers. They represent a function, and they're always changing. So let's move on and kind of introduce the idea of the summation piece in terms of how we're going to apply it today. And we're looking at, it's similar to summation, the sigma summation, because we are going to be adding a bunch of pieces together, which is why the sigma notation comes in handy when we transform that then to the integration symbol. So for this example, a train moves along a track at a steady rate of 75 miles an hour. So first of all, these problems are different than what we did when we were taking the derivative, because now they give us the rate. So we are working with functions that are in terms of a specific rate. If it were back in the derivative, that might be a height or some position, but in this case, it's the rate of change. So that's huge to understand, because when we're looking at the integral, we're given the rate versus the position. So it's rate over time versus position over time, right? Because this is the derivative now that we're looking at, which gave us the rate. So from 75 mile an hour from 7 a.m. to 9 a.m., what's the total distance traveled by the train? So this is an algebra problem, right? So if we just set up a simple graph, and we're going to say that this is our y-axis, and this right here, that's beautiful, is going to be our x-axis. Okay, where our x-axis, remember, is always the independent, and time is always independent. So that is our time, and so this right here is going to be our rate, which in this case is miles per hour. And so that means our time is hours. All right, so if we go from, you can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and all the way up to 75. So if we just go, let's go by 25s. So 25, 50, 75. 25, 50, 75. Now if we look at this problem, between 7 and 9, they are going 70 miles, and that's all we know, between 7 and 9. So here's 7, and here's 9. So our graph would look something like this. It'd be a piecewise because we don't know anything about that, right? So that's our graph. If we wanted to find the total distance, well, you know how to do that. Distance is equal to rate times time. So if we find the distance, it's rate times time, right? But think of it this way. So now we're going to move into the idea of the area on the graph. Now, when you take rate times time, what you are doing is you are taking you're finding the area of that particular rectangle, right? Rate times time. So the area of this rectangle is going to be 150. And in order for this to make sense, remember, so if you have rate times time, you would have miles and then hour. So you would have 75 miles per 1 hour times it would be 2 hours, right? And that's where your hours would cancel and you would have 75 times 2, which is 150, and that's why we're left with just miles left over, which happens to be the area of that rectangle, right? So that is a huge concept that we're going to be getting into, is the idea that the area on the graph, when you have a rate time graph, gives you the total distance traveled. Now here, an algebra student could solve that, but what about a problem like this? Like, what if you wanted to track that train throughout time? Obviously, that train is going to start at 0 miles an hour, and then it's going to increase speed, and then it's going to level off. Maybe it slows down, then it increases speed and levels back off. Now, with algebra, you cannot estimate this, right? And you wouldn't want to even try, because if you tried to estimate it, your estimate would look something like this, because that is a rectangle. Okay, now that area is going to be too high because we have stuff under the curve that we're including. So just like if you were an astronaut flying into space, your rocket is not going to fly or go at a steady speed the entire time. So you're going to want your people on the ground in Houston to know what in the world they're doing and use calculus to solve the problem, because not everything moves in a straight line. Stop this video here. In the next video, we're going to go into upper and lower limit approximations, which I call LRAM, RRAM, or I've called LRAM. Then we'll do a couple different examples of using those rectangle approximation methods in the next video.